we will this lecture will introduce you to dynamical systems. We'll start with something extremely simple, and we will and proceed. And okay, so instead of giving definitions, etc., so we start with an example, and the example is the following. Let X denote a measurable quantity in some system that we wish to study. It could be the position of a particle moving in one dimension. It could be the number of bacteria or the quantity of reactant in a chemical solution. So this X can take a bunch of possible values, and that set of all possible values, we will call that phase space. Okay. So this is a very, very broad definition. And so, for instance, let us suppose that X belongs to R, that means a real line, or even some subset. And so what we do is we draw, below I have drawn a blue line, straight line, which goes out to from plus infinity to minus infinity, and that is the phase space of the system. And so the idea is that dynamic. So this is the static part of the system, which says that what are the variables that I'm following. And so in this case, that's just one variable which we called X. Dynamics tells you how the system will be. If you know its value at a given time, what happens later, or if you go backwards in time, where did it start from? These are kind of things we would like to answer. And so we wish to model the time evolution of the system, and what does that mean? That means you have to determine the function x of t. So a simple family of examples is provided by something like this. Yes, a first order ordinary differential equation, dx by dt, that's the time derivative of x, evolves according to this function, which is a function of x and t. So let's write something. I'll write it like this. So this is this thing. So this function has two time dependencies. This one is called implicit dependence because it depends on t through x, and this is explicit. So both possibilities can happen simultaneously, and so I don't know how to, you can see that I don't know how to move it. I'm getting a line. So let's, just give me a second. It's annoying that there's this thing blocking. Anyway, and it's also not fitting in the thing. So let's look here. There's some three dots. Add to shortcuts. Enable S10 only. Okay. I think I know what I should do. Yeah. Sorry, like I said, it'll take some time. So we will call a system autonomous if it has no explicit time dependence. As you can see, I'm messing up. Okay. So in other words, this f of xt in the most general form here, as written here, as both explicit and implicit time dependence. A system is autonomous if it has no explicit time dependence. Okay, so this is the statement. Okay, so let's so we'll focus for the next few minutes at least for the autonomous case, and then we can do this given the value of x at some initial time t equal to t naught. We'll call that the initial state of the system. We can determine the state of the system at times t greater than t naught by integrating the time evolution of d. So formally one can write something like this. T minus t naught is this integral So how would we do this? We just write it like this, right? So dx by dt equal to f of x. So you rewrite this as dx by f of x equal to dt, and then do the integration. Okay. So this is what this thing is. Okay, so here I have put in some, so we are given this data, so limits come, so at time t equal to t naught, it's at x naught, and at time t it will go to x of t. So this is what input we have to give, and x of t is what we want. Okay, so this is a formal way of writing it, and suppose we can do this integration, and this thing. So you can also do integration backwards in time by just changing the limits. Okay, so this function x of t, we'll call it the phase trajectory of the system. Okay, so are there any questions so far? These are a bunch of definitions, but simple things.
So the function f was also a function of t, if I remember correctly.
No, in the autonomous case, it's not. We are doing in the autonomous case, we said there is no explicit time dependence.
Okay, sir.
Okay, so in the non-autonomous case, where there's explicit time dependence, what I have done won't work. Right? Because there is t on the left-hand side also. I mean, here what has happened is, see here, I mean, once we came here, you see that there is no time dependence on the left-hand side, so we can do the integration.
Okay, sir.
Okay? It's more complicated.
Where the function f is determined?
It's given to you. It's given to you. So my dynamical system has, in some sense, 1 degree of freedom, which we'll call x, and its time evolution is given by dx by dt equal to f of x. That is the time evolution. So you have to tell me what f of x is. If you don't give me f of x, it's then there is nothing to this problem. I mean, we don't know how. We need to know. Okay. So we are assuming that we are given f of x. Okay, if you're modeling some other system, then you have to, there might be some, suppose we were, studying growth of bacteria and something, then f of x, you will need to know some biology or chemistry, and to be able to guess or determine this f of x. So it depends on your system, what you're trying to model. So here we are doing something where we are assuming that hard part, actually that's a very hard part, that hard part has been done, and we have been given this function f of x. Okay, so let us look at the zeros of this function f of x. The reason will be clear in a moment. So let's say f of x vanishes for x1, x2, so on and so forth. Okay, so these are called the zeros of this function f of x. And these are fixed point, these are called, these are fixed points under time evolution, because, why is that? Because dx by dt with initial time naught, if it is equal to x1, if x at t naught is equal to x1, then x at t equal to x1 for all time. Okay, so that's why it's called a fixed point. Okay. So what we're going to do now is to start working through some simple examples and proceed from there. So we'll consider a very, very simple example first. Okay, so we'll play with some f of x's. So the first one we're going to play with is, why am I not able to move it now? Okay, anyway, okay, f of x equal to a, and so now the solution is very simple. It's just this. You can do this integration. F of x here is this is just what do you call, a constant a. So if you just go ahead and do this, you can do this integration. It will be just x of t, the x of t minus x of t naught upon a, which you can rewrite like this. Okay, so the initial condition that it was at x naught, you have to give me that thing where it is. Only then we can give. So we need to provide x of t naught to get the solution. If you don't give that, so but this is like an integration constant. Okay, so let me do this. So now if I write with my hand, it doesn't mess up. See, I'm getting clever. Okay, so let us now consider the case. Let's see if we can reduce size bit. Yeah, we can. Is this okay size? Because we can see the full.
Yes, sir.
Okay. So now we'll make it slightly more complicated. Previously we did f of x was equal to a. Now we will put some linear dependence on x. So it's some b of x plus a, and b should not be 0. If b equal to 0, it goes back to the previous case. So then you find that there is one fixed point, which is x equal to x1 equal to minus a upon b. And what we will do is we will indicate that in phase space. So remember, phase space was this straight line, and so it was, so this point is x1. So that's a fixed point. So now what we are going to do now is to ask, what happens if a point is very close to x1 but not equal to x1? How does it evolve? Okay, so we will assume, we'll consider a case where x of t, so this should be lowercase x1. So x of t not equal to x1, we can again integrate this function. So t minus t is not 1 by b into this thing, and you will find that, and we'll do it in the neighborhood of, did I make any approximation here? No, I didn't. Okay. So then what we get is something like this. We get a nice, we're able to do this integration. We get x of t minus x1 is equal to x of t naught. So if you wish, you could say that we can define a new variable y, which is x minus x1, and then this equation will look like y of t equal to y of t naught times e power b into t minus t naught. Okay, so this is what we get. But you look here now, so what we see is that, so there is an exponential dependence on time, right? E power b times t bar. So what happens if b is greater than 0? So if you, excuse me, let's try a different color now. Suppose you pick a point here, and what does this say? And b is positive. So if you, so at t equal to t naught, we were at this green point, and you can see that what happened? Sorry. Let me go back to that. Okay. Good, we got back this time. Okay, so we were looking at this particular case where, okay, where is the green pen only. So what happens is b is greater than 0, at some later time it will move in this direction. It will move away, and it will exponentially go away, far away. So this arrow, and you can see that it really doesn't matter, where this green point is, as long as it's on the right side of this red point, the fixed point, it will go to plus infinity. And similar thing is, if you consider a point here on the left side, it will go off to minus infinity. Is this clear?
Yes, sir.
Okay, so this is what is captured by this thing. So this is what happens. So we say in this case that the fixed point x1 is unstable, because if you take even a point arbitrarily close to it, it goes away from it. Okay, so that's what is happening. That happens for b greater than 0. But of course, we can also have b less than 0. And then what we see is that points which are close to x1, so they don't diverge, they converge to x1 exponentially in time. So now what happens is that it gets closer and closer, and at t equal to infinity, it will go and hit the fixed point. Okay. So then we say, so again, let me do this. So the fixed point is stable. Is this idea clear? So if you look at a fixed point and look for points close to it, in this case anywhere, you will see that it's either diverging, it's either stable or unstable. These are the only two possibilities, and that is fixed by the sign of B. Sign of A is not important in this. Is this point clear?
Sir, you say the points close to X. Does it necessarily have to be close? Because
No,
it's,
in this example, no. But later when we will see in the next example that there are multiple fixed points, and then we will do the analysis in the neighborhood of one fixed point. Okay.
sir.
So, okay. So we'll linearize and we'll map to this. But in this case, you're absolutely right. All it matters is, are you on the left side or on the right side? That's all. In this, for linear case, that is true. Because you can see when we did the integration, we didn't do any approximation. It's exact. Okay. So good.
So at x1 the particle stops. Means
It takes
we
infinite
consider
time. It takes infinite time.
okay. Means it will gradually move towards the stable point for the
Yeah. Correct. Okay. So now we make it more complicated, and so we look at a case where it is quadratic. Okay. So now we have cx squared plus bx plus a, and we'll again assume c is not 0, because if c is 0, it goes back to bx plus a. Okay. So now we'll have to consider. So first thing is, so let us consider the case when when the discriminant, which is b square minus 4ac, is greater than 0. Okay. So then we know that so fx equal to 0 is just the roots of the quadratic equation. And so lo and behold, we get two fixed points, which we call x plus and x minus. Okay. So now it's more complicated to do the analysis. And what we will do is we'll expand f of x in the neighborhood of the fixed points. Okay, so you can just go ahead and do Taylor series. So this is just Taylor series. First term, first series, first non-trivial term. Right, because f of x, so a Taylor series would have been f of x equal to f of say x plus f prime at x plus x minus x plus. So this is, so you have to do just, this is just nothing but f prime at x plus minus. Just a calculation. You just take the derivative, you will see it. Right? Take a derivative, it is 2cx plus b. And you put in the value. Okay? So that's all this is. Is this clear what I'm doing? So now, what we are doing is looking now, if you look arbitrarily close to x plus, or let's fix on x plus, say. If you look at points x which are arbitrarily close to x plus, then it looks exactly like the previous now. It looks like this. Okay. And what did we see here? It said that the coefficient, so you look at the coefficient of x, which is b in this thing. So we have to compare here. So what would be the coefficient of b here? It would be this constant, right? What is, we should call it b hat or something. 2c x plus b. So for small x minus x plus, the sign of 2c x plus b determines whether x plus is stable or unstable. So now I have to qualify what I say is that I should go to points which are arbitrarily close to x plus. So something, so I will have to choose something like this. Okay, something close to x plus, and ask what does it do. And I have to choose my x such that this Taylor expansion is a good approximation. And if you make it arbitrarily small, it will be a good approximation. Is this clear? Okay, so now, so one more trivial property which says that, so if you go to x minus, now you have to the sign of 2c x minus. So here 2c x minus plus b, the sign of this determines whether it is stable or unstable. But now you look at these two numbers, and if you just look at, if you work out you know what x plus and x minus are, you can verify that this is true. So what does this say? If 2c x plus b is greater than 0, what can we say about 2c x minus plus b? Anybody?
Will be less than 0.
0. Okay, so what does it say? Is that it says that one of them will be stable and the other will be necessarily unstable. Okay, you cannot write something, at least for the discriminant greater than 0. And so I have drawn some figures for C. I have assumed C is greater than 0, I think. And okay, so here we can see that so locally so here you can see that this is stable, but here this is unstable. And smoothness of the function tells, actually I have drawn, now you can see that I initially said that this happens, but you can check that this happens even now if you go arbitrarily far away, that this happens, but this will require full nonlinear analysis, but still it will happen. Okay.
So, here by fixed point you mean a point where fx and thus dx dt is equal to 0, no?
I mean, yeah, fx, so x plus and x minus are where so f of x plus is 0, f of x minus is 0.
And so if x is the position, then that means the velocity of the particle is 0 at that point.
Yes, yes.
But by stability we often mean that the acceleration of the particle must be 0. Then we mean that the point is stable.
No.
Because at an
no. It's what I'm saying. It's stability is nothing to do with acceleration or anything. It has to do with a family of trajectories. So see, there is one trajectory which is one trajectory which is x equal to x plus, which is just a constant, 1 point, right? It remains at x plus. But then you take something nearby and ask what does it do as a function near x plus, and ask what does it do. And so this linear analysis tells you that it goes towards, in this case, in this example, it goes closer and closer to x plus and will reach x plus at, it will take infinite time, but it will reach. Okay. For me, stability is a property of a family of phase trajectories which are close, whether how they behave.
Sir, I think what he meant was equilibrium.
Yeah, but this is not okay. This has nothing to do with that. This is just a property of the fixed point. We will discuss equilibrium and all later.
Okay.
Yeah. So this is a very, very elementary statement. Okay. Oh, okay. Thanks for clarifying that. But equilibrium is also a property of this thing. Okay. So now the next question to you is, what happens when b square minus 4ac is less than or equal to 0? Okay. Any ideas?
Sir, x will be complex. Right.
What will happen? Are there fixed?
The roots of the equation will be complex numbers.
Yes.
B square minus 4ac. So maybe there are no fixed points.
Absolutely right. So there are no fixed points. So, but there is a very nice geometric story in this whole thing. Is that let's start with the discriminant being positive. Okay, b square minus 4ac, and slowly, let's say we reduce b or whatever, we play with some parameter. Okay, and we reduce it such that it comes to 0. So slowly we are reducing it. Then what happens when it is 0? Both x plus and x minus coincide, right? So what happens is that in that process, x plus and x minus are going to the thing at exactly 0. They sit on top of each other. So okay. So then the picture. So maybe I have that. I don't know. I forgot it. Okay. So what would be the picture then? So when x plus equal to x minus. So if you take the top guy, what we will see is that they coincide, but the arrows will be the same. So this is what will happen for the top one. So if you put a particle, it will move leftwards. Okay. Little bit of thought will show you that then after that, so when now we take it negative, that means there are no more roots. So this plus will also disappear, but I claim that the answer will look like this. Is this clear what I'm saying? So the first picture is for x plus equal to x minus, which is when the discriminant is 0. And the second picture below is the case when the discriminant is negative now. So there are no these things. So there are no more fixed points. But this feature which we saw will continue. Okay, so that it will give. If you want to try the flow, if you put what it says here is if you start with some point here, it will move to the left. Similarly, for the bottom diagram, it will move to the right. Okay, so please go ahead and play with these things and see for yourself whether what I'm saying is correct. Okay.
Also, sir,
Mm-hmm.
so the question of stable and unstable comes only for fixed points, like
Yeah, in the neighbor, exactly. It's a statement of the fixed point. It's statement of about trajectories which are close to the fixed point.
Okay, sir.
Okay, it's a property of the families of trajectories which are arbitrarily close to the fixed point. It's not about just x plus, because we need to look what happens if you push jiggle away. Okay. So in that sense, it is like equilibrium, something coming back, Okay. So what about general f of x? How would we proceed? Okay. So step one is first you determine all the zeros of f of x. Okay. And let's assume there are s of them. So we call them xa, a equal to 1, 2, 2 up to s. For each xa, you study the sign of f prime of xa. If it is positive, it is unstable, and it is stable if it is negative. This is just repeating whatever we did earlier, right? We just saw. So we are just looking at the neighborhood. So this is your thing, and this is xa. So we just look very, very close so that Taylor series to first order is good. If f prime of xa is 0, then you need the next term in the Taylor series, of course. This means one has a 0 of higher order and more analysis is required. Okay, but it's not that much more. We have already seen what happens when two guys coincide. So it's a 0 of higher order, right? So that's what is happening. And so you if you have, if it is going to, so if the first f prime is 0, but f double prime is non-zero, that means it's like two zeros have collided. Okay, so the pictures, you can actually extrapolate these pictures, but I will leave that. But all I'm saying is further analysis is required.
So did you choose ax square plus bx plus c just as an example, or is there any reason?
Oh, I just made it more. No, I just chose it as more. I made it more and more complicated. So 1, 0, 2. First is no zeros. Second was 2 zeros. 1, 0, 2 zeros. That's all.
Okay.
Okay. So, and of course, yeah. Okay. So if the 0 is of order 2, that's what I'm saying here. It can be thought of as a limit of two fixed points coinciding in the just as in the quadratic case that we just considered. This happens when the discriminant b square minus 4ac vanishes. But this is actually, I keep saying this, but it's a very nice exercise. Show that it takes infinite time for the system to approach the coinciding fixed point. Okay. So what I'm saying, yeah. So here you're coming here, right? So you can ask, how much time. So if I start from somewhere here, how much time will it take to come here? Okay. But in fact, this can be true even for a single fixed point. If you start from here, ask how much time will it take to get to x plus. Okay. I claim it will be infinity. Okay. So now exercise for you is to consider more complicated things. Okay. I did simple things. So first one is, consider f of x equal to x cubed minus x, or f of x equal to 4th power, but I given something of a particular kind, x square minus 4 whole square. Okay. So this is for you exercise. Determine their fixed points and study their stability. Okay, stability is always going to be local analysis. Local means in the neighborhood of that fixed point. Okay, so I'll pause here before going to more general things, asking for questions, comments. Okay, I guess everything is crystal clear. So let's go to the next. So we look at more general. Yeah, go ahead.
Sir, I have a doubt. What will happen if we are at the fixed point?
Nothing will happen. You will just remain there.
Okay, so no.
Yeah, that's why it's called fixed point. Absolutely, absolutely. Okay. Okay, good. So obvious generalization is to have many variables. So in this case, we have x equal to x uppercase 1, x2 up to xn transpose. So you write a big column vector with n elements. And then we say that the phase space is n dimensional, and we call x the state vector. So if you want to specify your system, what is it at, you have to give me n numbers. Okay. So phase space is n dimensional. And now we need to give time evolution. So we have to, we want to do a simple time evolution. And I'm drawing autonomous case here. Still autonomous. No explicit time dependence. So I'm asking for n functions, f1, f2 up to fn, which will tell you this thing. So you can write an equation of this variety. So these are n first order differential equations. And they'll be coupled because these functions f1, f2 up to fn, they depend on all the n variables in general. Okay. Nevertheless, there are some nice properties, and this is just simple, differential equations from mathematics. Given n initial conditions, so because we have n integrations to do, we'll have n integration constants, and that we will change into, that we will give in the form of n initial conditions. If you remember in the previous case, we just gave x at t naught. But now we have to give x1 at t naught, x2 at t naught, xn at t naught. So n numbers we have to give. Okay, so this will be a point in phase space. Okay, and the key point is the evolution is unique. Okay, the second property, this uniqueness implies two distinct phase trajectories can never meet. Okay, why am I saying that? So let's assume they meet. So let's say that this is one phase trajectory and this is another phase trajectory. They're crossing here. Okay, so now I can ask, go back to the first condition and pick this as my initial condition. And what this says is that the evolution has to be unique. So you can't have, sometimes it will go this way, sometimes it will go this way. This is a deterministic equation. So this cannot happen. This kind of thing cannot happen. So this is the thing. But there is one case where it looks, yes.
So this trajectory is drawn with what axis?
No, it's in some n-dimensional space, so I'm just drawing some projection onto my plane. I'm just saying they are meeting. Okay. So this kind of thing cannot happen because it violates the uniqueness theorem which we just saw. Okay. But there is a second case which is very interesting. Suppose this is a fixed point, and then let's say we have two trajectories. One like this, coming one like this. Okay. This again in higher dimensions it might be possible, not in 1D which we did. Okay. So but now the point here is that this is a fixed point. So if a particle is there, it will remain there. And so now what is happening is really that I have a trajectory which seems to be ending here. That is allowed. The reason is how much, as we in the 1D case itself, we saw that if you're approaching a fixed point, it takes infinite time. Okay, so the trajectory, this is a trajectory for infinite time, and the point, the actual end point, the fixed point is actually not in that trajectory. So this is the thing. Also, it says that a single phase trajectory cannot self-intersect. So something like this also cannot happen. You can see that again, that is a contradiction. Okay. So is this clear? So this is just an elementary property of differential equations. First, this is first order differential equation.
The uniqueness property is assumed, or
which one?
uniqueness property, that time evolution is unique.
Yeah, I mean, but yeah, I mean, yeah, it is assumed, but it is a standard mathematical fact. That's all. It's a fact of differential equations.
Sir, if they can come and end at a point, why cannot the right side graph happen? I can explain that also as they approach arbitrarily close but
No,
never
no, yeah, yeah,
touch.
yeah, no, no. But what I'm saying here, it's as if there was a trajectory, one trajectory like this. This is the second trajectory. If you're going to tell me these are 4 trajectories, then I'm okay with that.
Okay.
That is possible. Okay. So again, we can look for fixed points, but now fixed points will be solutions of n simultaneous equations. So f1 of x should be 0. At the same time, f2 of x should be 0. All of them should be 0. It's not enough if just f1 and f2 are 0 and all the others are non-zero. That won't be a fixed point because other things are changing. Okay. Is this clear? This is just simple. Okay. Now stability is studied by studying the matrix of first order of partial derivatives. Why is that? So what we have to do really, I'll explain that below. So that's fine. Okay, so now if you again Taylor, so again, everybody knows Taylor series, right? Hello?
Yes.
Is there anybody who's never heard of Taylor series?
Yes, sir.
Okay. Yes means what? You never heard of Taylor series. Or yes, I've heard of Taylor series.
We have heard.
Okay, very good. Okay. So unlike the one-dimensional case that we studied, that's actually a much, much richer structure. And this is true even in 2 dimensions. So what you do is the general analysis is carried by studying the Jacobian matrix. So that is, so there are n functions and n variables. So this is an n by n matrix. Okay. And this you evaluate at the fixed point. Okay, so if you, a little bit of thought will show you that this, what will happen is fj at any fixed point, let's say x1 is a fixed point, that will be x minus xi minus x1i. That's what, and this will be evaluated at x equal to xi, x1. Of course, summation over I is implicit. So this is the first order Taylor series. And you see that this matrix that you get is this J. Okay, so first thing is that one can bring a Jacobian matrix to standard form by linear change of variables. And in some cases, it makes J diagonal. In other cases, it will be Jordan canonical form. That's the best you can do. And we will discuss this system. So what I'm saying is that let's say we take 2 by 2. Okay, so you could find J. There will be some change of coordinates in 2D such that at that point only it will look like this, some diagonal elements. But it could also be something like this. So Jordan form in 2D with something like this, DD, and something non-zero. You can bring this is the best you can do. Okay. So we will consider these things later in the course, but I'm just showing you that it gets much, much more complex. Okay, so again, I'll pause here and hopefully you understand, I mean, roughly what happens in higher dimensional case. And it's more, more complex, but much more fun. I mean, in some sense, 1D is boring. Okay, so are there any questions?
So where does this idea of Jacobian fit into the analysis of one-dimensional case?
Here, if you just did Taylor series to first order, because f of x1 vanishes, fj of x1 vanishes for all fj, So the first non-trivial term will be j times x minus x or x1. So formally, that's all. F will look like j times x minus x1. I'm hiding indices.
Where J is df by dou x. That's all.
Yeah. df by dx. Yeah, absolutely. Okay.
Hello.
Yeah. Go
Sir,
ahead.
could we get a reference book or something so that we can study it more clearly?
No. No. I mean, I think it's time to stop looking for reference books. Take and work out some examples. Okay.
Examples.
Yeah. We will do enough of these things. So, I mean, at some point, we have to stop. That's a very bad habit. I mean, all of us had as students. I'm not blaming you alone. Is that you will always, if you're given something to do, you will go look for a book where it is there. No, I mean the whole point is that about doing science is that most of the time you are doing things where things are unknown. Okay, so in this case, these are not. I mean, these are all simple ideas which you would have learned in your BSc Maths. Many things you would have done in your BSc Maths, a Maths course in your BSc. Or in some other, okay, and then you just are using those ideas. I mean, so these are tools, and there will be. I'll give you one reference if you wish, but my point here is that what I'm saying doesn't require, I have never learned this from any book. I mean, I don't need it. I mean, I'm just taking known math and putting it in here. Okay, just once you give me this thing and I'm analyzing it locally. Okay, so we just do examples. We will have in the problem sets. We'll have some things, and so. That's what you should do. I would recommend that more than. Okay. So quite often, what happens is that you might be interested. So you have a system and you have a bunch of variables, which is this vector x. I'll put as under. I can't write boldface x, so I'm writing it. But what you are interested might be some other property which is a function of x. So that's what I have written here. So you consider, so you're interested in some arbitrary function of g of x, and it could have some explicit type. So this is what might be the object of interest, let's say. Okay. So what we might be asking, sometimes we are interested in asking, can we find a function g such that as the time evolution of x happens, it doesn't change value. Okay, that means, so a constant of motion, it remains the same along the phase trajectory. So where it doesn't matter where you measure. At any time you measure, you get the same value. Of course, if you go to a different phase trajectory, you will get a different answer. But again, if you stay inside that phase trajectory, okay, then what will happen is that it will not change. So this is just again nothing fancy. dg by, we want to ask how g varies with time. So this is explicit time dependent. So that will give you a term like this. And then dg by dx times dx by dt. So this is just the chain rule. This is the second term. But we know that dx by dt is given by phi. Okay. So if it is a so this is just, so until this point, is just the statement of dg by dt. But if it is equal to 0, then we call it a constant of motion. Okay, so this formula which go ahead.
Sir, is this phase trajectory the same that we call trajectory usually? Or is this like...
Yeah, it is called the same. It's the same. I mean, I don't want, no, in some sense.
I mean, there are two things. First,
see, yeah, so what I have in mind is phase trajectory need not be trajectory, because in usual classical mechanics, the phase space will be twice the dimension of your coordinate space. So trajectory, we usually talk about something in just coordinate space.
Yes.
Okay.
So is this the one from the position and momentum space?
No.
Exactly.
Space? Exactly. Yes.
Okay.
Good. Very, 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 very good question. So that's why it's phase trajectory, not.
Okay.
So x can be any thing, but t is time.
C is time. Absolutely. Yeah. Okay, so quite often we'll be looking for functions which don't have explicit type dependence. So the red term here, this term drops out. So we just get this as a condition. Okay. Of course, there may be no such, it doesn't follow that there exists such a G. So if we can find such a G, okay, so may not exist. Okay. But when it exists, it implies that the phase trajectory is restricted to hypersurfaces of Gx equal to constant, but the constant is determined by the initial condition. Okay, so the picture I have in mind is, suppose this is your phase space, is two-dimensional, and G of x is, so you will find that you draw different lines for different values of G equal to different constants, and then you will find that if you give me some phase trajectory and it takes values here, it will continue to move inside that in this line. It can't leave the space where that G is constant. Okay. This is a trivial statement, but it just tells you that this is what will happen. Okay. So now let us get to our Newton system, and you will understand why. Okay. And I'll be done after this. Consider a particle of mass m moving in space under the action of a potential v of x, and Newton's equations is just m d square xi by dt square equal to minus gradient of this potential. Okay. So first thing is, it does not appear to be like an autonomous first order equation. So what we can do is we just add more variables, 3 more variables in the form of momenta p equal to m dx by dt, and now you will find the autonomous form of Newton's equations to be this. So this is, you can see here, this is a 6-dimensional phase space. Okay, and so now to solve this thing, this equation, this 6 initial conditions are then given in the form of the position and momenta of the particle at time p equal to t naught. So this actually addresses somebody's question. So you see, when I say phase trajectory here, you can see in Newton's equations it means motion in that 6-dimensional phase space and not 3-dimensional coordinate space. So when we talk of constants of motion in this setup, it will be functions of not just x, but functions of p as well, functions of x and p. So here's an example. You define the function h of x and p, okay, which is p square about 2m plus v of x. This function is called the Hamiltonian, and its value is called the energy of the system. And it's a constant of motion. How? We just go ahead and do what we did before. dh by dt is partial derivative of h with respect to xi times xi dot plus partial derivative with of this thing with pi dot. And then what happens, you can check. So but we know these two guys, right? If you go back one page, we know dx by dt is p upon m and dp by dt is minus gradient of. So you plug that in, you will get 0. So energy is a constant of motion. The Hamiltonian is a constant of motion. And its value it takes for a trajectory is called energy. Okay. Exercise for you. Consider this function g of x p t, which is xi minus pi t upon m. See that it's a time independent. It's a time dependent now, because there is a time dependence here, constant of motion in the absence of forces. So for a free particle, exercise for you. Okay, so now we will, somebody was talking about states of equilibrium, etc. So what is the fixed point of the Newton's equation? So let's go back. So it would say that set the right hand side to 0. Right, that's what it said. All these, so 6 functions should vanish at the same time. So let's do that. So p upon m should be 0 and minus gradient of this. So what are the solutions? So these corresponds to the points in phase space with P equal to 0 and extrema of the potential. Is this clear? Any questions? Okay.
Yes.
So we all the time when we in your BSc days or in earlier classical mechanics classes, you would have one tends to forget this condition and just write gradient of Vx equal to 0 and you solve it very, very fast, I'm sure you people can do it faster than me, but you will forget that that's a condition, 3 other conditions where P1, P2, P3 should be there. And the stability of the potential is carried out by studying the derivatives with respect to all 6 variables. But there is some simplicity in this whole thing, okay? But so in order to study the stability of the fixed point, P, which would be x equal to some vector x1 and 0 in phase space, we need to study of the behavior in the neighborhood of this fixed point in phase space. And one needs to account for the constant of motion called energy. And this is something we will discuss next lecture. So I'm done for today. So what we have seen today is first we started out with a simple idea of a dynamical system and the idea of fixed points and whether fixed points are stable, unstable. And then we generalized it to having more and more variables. And then we also saw that Newton's equations for a particle moving in a potential fits into this scheme of things. Okay. But so the thing is that Newton's equation is a very simple, is in some ways a very special kind of dynamical system, and we will see in what way it is special in the rest of the course. Okay, so I'll stop here. Any questions?
So momentum being 0, isn't it a property of our reference frame? If we go to a different inertial frame, then maybe it is not.
Now you are getting very, very fancy. I mean, I'm in one frame.
Okay. So we choose the frame such that P is 0. So
yeah. I mean, you can ask yourself what you have to do to the equations if you are in another frame. Okay.
Right.
Yeah.
No.
See, energy. Yeah. Go ahead.
Sir, if energy is the value of Hamiltonian, then
evaluated on the phase trajectory. Yeah.
Why do we have two names for?
Delhi, very, very good question. Okay. One is a function, the other is a number.
Oh.
Hamiltonian, right? Hamiltonian is a function of 6 variables in this example. Energy is just a number. You give me the phase trajectory, you put all those things in, and bingo, you get a number. So actually, I in fact said that. Maybe it went too fast. And its value is called the energy. Okay, a very, very important point and a very good question. Okay, anything else? Okay, so then let me stop recording.